Now in this module I want to discuss the topic of heat and temperature. So what is the difference between heat and temperature? Well, heat is a form of energy that is stored in a body when its temperature rises. And the temperature is a measure of degrees of how hot it is. So in other words, how much heat it's got in it, but temperature is just a measure of that. Heat is the actual energy. For example, a cigarette end is very hot, but it does not hold a lot of heat energy, whereas a brick removed from a furnace is not only hot, but it has a lot of heat energy. Now, to talk about temperature and heat, we need to understand the Kelvin scale. So to understand this, you need to know how hot something is, you need to know the Kelvin scale. Now, temperature is actually measured on the temperature, the Kelvin scale, and this was developed by Lord Kelvin in the mid-1800s, and the 0 point of the scale is equivalent to minus 273 degrees C. So 0 degrees Kelvin is minus 273 degrees Celsius, and this is considered the lowest temperature of anything on our planet. You can't get anything colder than 0 Kelvin, which is minus 273 degrees C. Therefore, the Kelvin scale is also known as absolute zero, or the absolute temperature, and it's the point when the molecules have absolutely no movement. So if you can cool something down to minus 273 degrees C, which is 0 Kelvin, those molecules will not vibrate at all. They'll have no kinetic energy. In other words, it's the lowest attainable temperature. Now, at the boiling point of water, it will read 373 degrees Kelvin. Do you understand? 100 degrees C is 373 degrees Kelvin. Now, whereas the Kelvin scale is widely used by scientists, the Celsius or Fahrenheit scales are used in daily life. And these two scales are easy for us to understand. Could you imagine walking up to your radio and hearing the DJ say, "What a lovely day it is. The temperature outside is 297 degrees Kelvin." What would people think? What does it mean? Well, that is 24 degrees C. Do you understand the difference? Well, you need to understand Kelvin because all formulas are based on Kelvin, but we actually do sometimes equate it back to degrees C so you understand it. So you've got to convert formulas. When it's in temperature, you will have to convert to Kelvin. So, at minus 273 degrees C, at absolute zero, at this point there's no movement of the molecules at all, and everything on our planet would be in solid form. So at 0 Kelvin, every single thing on our planet would be a solid. So chlorine's a solid, water's a solid, and steel is a solid. Now, as you start to heat these up from this temperature, they'll start to change form. They'll start to get more energy and start to consider changing from a solid to a liquid. Now, the melting point of chlorine is 172 degrees Kelvin, which is minus 101 degrees C. So if you heat up these three elements up to 101 degrees C, the chlorine will turn into a liquid, so it will turn from a solid into a liquid. The water and steel will still be in a solid form. Now, the boiling point of chlorine is 239 degrees Kelvin, which is minus 34 degrees C. So if you heat all these up to 34 degrees C, what will happen is the chlorine will change from a liquid to a gas. However, the water and steel will still stay as a solid. Do you understand? As you heat something up, it changes form. It depends if it's got a high melting point or a low melting point. Now, if you heated all three substances to 273 degrees C or 0 degrees C, then the water would turn from ice to water, liquid form. Do you understand? It would start to turn back to a liquid, but the steel would still be a solid. So do you understand that substances turn from solid to liquid at their melting point and from a liquid to a gas at their boiling point? That's how it works. What you generally find is that gases on our planet, such as hydrogen, chlorine, carbon dioxide, etc., all have very low melting points and they all have very low boiling points, whereas metals have very high melting points and very high boiling points. Now, there's a few definitions that you need to understand when we're talking about heat. Now, firstly, as we mentioned earlier, that minus 273 degrees C is 0 Kelvin. So as we start to heat it up, it reaches its melting point, and it'll start to change shape, state from a solid to a liquid. Now, to change from a solid to a liquid, it requires some heat, and this is called latent heat. What it means is this heat changes form, but it doesn't change its temperature. So it stays at the same temperature, but it changes form, and it changes state. So from a solid to a liquid, this is called the latent heat of fusion. And this is the amount of heat to change 1 kilogram of a solid at its melting point to a liquid, but the temperature remains the same. So it doesn't heat it up. The latent heat of fusion is the energy required to change from a solid to a liquid at the same temperature. Do you understand? It's at the same temperature. Now, once the solid has changed to a liquid, then it will be heated to its boiling point, and this requires more energy. And this is where we get the specific heat capacity of the substance. So the specific heat capacity is the energy required to raise its temperature. Now, once the temperature has reached its boiling point, it's got to convert from a liquid to a gas. And this is known as the latent heat of vaporization. And this is the amount of heat required to change 1 kilogram of a substance at its boiling point to a gas. So it changes from a liquid to a gas, and that's the latent heat of vaporization. What temperature increase will we have? None. So the temperature's the same. But do you understand? Basically, you have the specific heat capacity, which increases the temperature. However, to change it, it's called latent heat, and the latent heat of fusion is the energy required to change it from a solid to a liquid, and the latent heat of vaporization is the energy required to change it from a liquid to a gas. That's what you've got to understand. Very important you understand that and when these substances change, heat is given off when a substance changes from a gas to a liquid, it gives off heat. Yeah? It's very important to understand that. Let's do an example to understand this. How much heat is required to turn a 2.5 kilogram block of ice at absolute zero to water vapour at 200 degrees C? That's the question. How much heat is required? You're given all this information. You've got the specific heat capacity of ice. That is how much energy is required at ice to heat its temperature up. Then you've got the specific heat capacity of water. You've got the specific heat capacity of water vapour, which is basically steam. And then you've got the latent heat of melting or fusion, latent heat of melting, and you've got the latent heat of vaporization. So you're given all this information. Now you've got to use that information to determine how much heat is required to turn a 2.5 kilogram block of ice at absolute zero to water vapour at 200 degrees C. Let's work this out, this example, and this should demonstrate the principles. Right, what's the first we need to do? We've got 5 steps here. Step 1, we've got to determine how much energy is required to raise the temperature of the ice at absolute zero to its melting point. Then we've got to convert the ice to water. Then we've got to heat the water to its boiling point. And step 4, we've got to convert the water to water vapour. And finally, we've got to heat the water vapour to 200 degrees C. Do you understand? We've got to work out 5 steps. And these 5 steps should make you understand this whole principle. Right, first of all, we need to determine how much heat energy is required to raise 2.5 kilograms of ice to steam. Well, the first we need to do is provide heat to heat the ice from 0 Kelvin or minus 273 degrees C to its freezing point, which is 0 degrees C. In other words, it's got to heat it up by 273 degrees. And how do you work this out? Well, this is a formula. The heat required is the specific heat capacity of ice times the temperature rise times the mass. So the heat required to do this is 2.108 times 273 times 2.5. The heat required to heat ice up at 0 Kelvin to 0 degrees C, in other words, at its point when it's going to turn to a liquid, is 1,438.71 kilojoules. So that's step 1. That's how much energy is required to do that. Now we need to convert the ice to water by applying more heat, and now the heat required to convert 1 kilogram of ice to water we said was 334 kilojoules. Therefore, to convert 2.5 kilograms of ice, we need 334 times 2.5. We need 835 kilojoules of energy. That is to turn 2.5 kilograms of ice into 2.5 kilograms of water. The latent heat of fusion, that's that. Now we've turned the ice into water, we need to heat it up now to its boiling point. This is where the specific heat capacity of water comes in. So how much energy do we need? Well, the heat required is the specific heat capacity times the temperature rise times the mass. Therefore, the heat required is 4.187 times 100 times 2.5. The heat required is 1046.75 kilojoules. That's step 3. So do you understand? We're adding all this energy together. Now we need to convert the water at its boiling point into steam. So now we need the latent heat of vaporization. Now we've got to turn it from water into steam. And the heat required to do this is the heat equals the latent heat of vaporization times the mass. Well, it's 2,270 kilojoules per kilo. You times it by 2.5, it takes 5,675 kilojoules of energy to turn 2.5 kilograms of water into steam. Now, that's actually why water should always be used in mist form or droplet size, because it takes a lot of energy to turn water into steam. It's very efficient at using energy, and that's why firemen should always try and get it into spray form to turn the water into steam. The last step, step 5, is to heat it up to 200 degrees C, the steam. And this is the formula here. The heat required equals the specific heat capacity of water vapour times the temperature rise times the mass. You put this in, it's 499 kilojoules. So we need 499 kilojoules to heat up water vapour at its, that's just converted 100 degrees up to 200 degrees. Now all we do is add up all the steps together. So we add up all these energies and we come out with 9,494.46 kilojoules. So the heat energy required to convert 2.5 kilograms of ice to water at 0 degrees Kelvin to water vapour at 200 degrees C is 9,494.46 kilojoules. Now don't forget, this works both ways. If water vapour at 200 degrees C was allowed to cool and convert back to ice to absolute zero, it would give off 9,494.46 kilojoules of heat energy. Do you understand? It goes backwards. So if you lose heat energy, you can't lose energy, it will give off that heat energy. So when something condenses, it gives off that heat energy. Let's do an exercise. Determine the heat which is released when a 3.4 kilogram brick, which has a temperature of 300 degrees C, is allowed to cool to ambient in a room. Well, ambient temperature, you're looking about 15 degrees. The specific heat capacity of the brick is 855 kilojoules per kilo per Kelvin. Well, the heat released is equivalent to the heat equals the specific heat capacity times the temperature difference times the mass. Well, if you put in known values, you get 855 times, that's 300 minus 115, that's your temperature difference, because the ambient's 15, times 3.4. You put them in, that's how much heat energy would be released on cooling that brick.